Right, let's do capacitors in series and capacitors in parallel. First of all, what's capacitance? Well, it's the charge stored per unit potential difference. Okay, so capacitance is charge per unit potential difference. You're given this equation. So when we've got a capacitor, if we've just got one capacitor and we connect it up to a battery, some charge is going to come around and sit there, and that's going to repel some electrons from there, and that's how much charge it will store. If we put in another battery, well, then another cell, sorry, then we've got more energy pushing these little electrons on. So if we double the potential difference, we double the charge stored. Now, you can, if we just rearrange this equation, I like it as Q equals CV. That makes sense, doesn't it? Double the potential difference on a capacitor, you'll double the charge stored. Right, let's see what happens when we've got series and parallel. So we'll start with parallel. Now, if I've got my cell there and I've got two capacitors in parallel, we know, because we know about things in parallel, that the potential difference over this one is going to be the same as the potential difference over that one, okay? Which is going to be the same as the potential difference, the EMF of the battery. So the potential difference is the same over each one. So let's have a look then about the charge that can be stored. We've got the charge stored is CV. So the total charge stored, well, we're going to have some charge stored on that one. We're going to have some charge stored on that one. So total charge would be the charge on the first capacitor plus the charge on the second capacitor. And that would give us our total charge. Now, we could write that, if we wanted, the capacitance, the total capacitance, times the potential difference, and remember the potential difference is the same over the battery, over that capacitor, plus over that capacitor, is equal to, well, Q1 would be capacitance 1 times potential difference plus capacitance 2 times potential difference. But these potential differences are all the same. We can cancel them out, cancel, cancel, cancel. Oh, look, we've got that equation. We know that equation. The total capacitance when they are in parallel is C1 plus C2, and that is why it's a function of the potential difference being the same over each one of them. Okay, so in parallel, charge can be different, potential difference is got to be the same. Okay, potential difference the same over each bit of the circuit, each branch of the circuit. You guys know that, we've revised that already. So let's have a look what happens when we've got capacitors in series. Okay, now what's happening when we've got them in series is this. We've got some electrons come round here. They sit on this side here. That repels the same number of electrons off this side here. The same number of electrons that get repelled here go and sit on this one. And again, da, 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 da. So the important thing is that the charge stored on this one is equal to the charge stored on that one. Okay, they're not different charges anymore, they're the same charge. Okay, so the charge is the same. Well, what's different though? What is different is the potential difference, because we've got a series circuit, and you guys know, because you revised potential dividers, haven't you, that EMF is going to be split over all the different things in the circuit. Kirchhoff's second law, remember, conservation of energy. EMF in a loop is going to be equal to the potential difference sums in that loop. Right, well, let's have a think what we know then. The potential difference is going to be different, but the charge is going to be the same. We've still got our equation, Q is equal to CV. So we know that the charge stored on 1 would be equal to the charge stored on 2, don't we? There's got to be the same charge. Now, if the charge is the same on 1 and the charge is the same on 2, can you see we've got this equation that the capacitance of 1 times the potential difference of 1 over 1 must equal to the capacitance of 2 times the potential difference over 2. Now look what that means, how that's going to split. Let's say C1 was big. Let's say it was 200 millifarads, and C2 smaller, it's 100 millifarads. We'd have 200 millifarads times V1 equals 100 times V2. Now, if we know what the total EMF is, V1 and V2, we could work out what V1 and V2 must be. Because look, it splits in ratio, but it's the difference to the resistors, because the bigger potential difference is going to be over the smaller capacitance. Okay, that should have an M, shouldn't it? But you're going to have V2 is going to be bigger than V1 in the ratio of 2 to 1. So it splits in ratios just like it does over resistors, like you've revised for potential divider circuit. But it's the other way round, okay? So the bigger potential difference over the smaller capacitance. Now, there's a way that I can show you how to find the total capacitance of this. Let me have a think. To find the total capacitance, it's to do with 1 over CT is equal to 1 over C1 plus 1 over C2. Just like resistors in parallel, you've got capacitors in series, and it comes from this really. It comes from working out that what would happen with these. But I'll leave going through that till after I've had my tea. Get revising. I'll see you all tomorrow. Period 1 and 2. Bye bye.